It is my pleasure to present Victor Franco Sanchez from the UPC, and he will show us a negative, very positive result, right? About not being able to optimally trek in the Alps.
All right, thank you. I'm very grateful to be here. So I want to talk to you about this very simple problem, and this is very simple to state. We're given a polyhedral terrain, that is a terrain that's triangulated. We are given 2 points in this terrain, S and T, and we want to find the shortest descending path, right? So, or at least non-ascending. This problem was defined in 1997 by Herrero, this paper called Trekking the Alps Without Freezing or Getting Tired. It's a very cheeky name. And they also defined the question of whether you can find, if there exists, a descending path from S to T, the decisional version of this problem, and they found out that this decisional version was easy, as in you can solve it in big O and log n time. But they were not able to solve this optimization version of finding the actual shortest path. This was in 1997, and since then, only approximation algorithms came out. We have these 2 algorithms by Ahmed et al. That have these very nasty variables in them. Like you have things you would expect, right? You have the number of vertices in the terrain, and you have the approximation factor in here. This is all expected. But you also have things like the length of the longest edge in the terrain, which is a little bit weak, but okay. You have the largest acute angle between a non-level edge and a vertical line. And you have the smallest distance of a vertex to a non-incident edge in the same phase. Super weird stuff, right? So this shows that there's something weird going on in this problem that makes it difficult to work with. And in 2014, we have the first standard-looking approximation algorithm with a standard-looking cost. So, yeah, we have not been able to solve the problem exactly, but we have been able to solve it exactly for certain families of terrain. For example, for convex terrains, you can solve this problem exactly. Also for pseudo-orthogonal terrains, these are terrains in which every face is either just perfectly horizontal or perfectly vertical. And also pseudo-convex terrains, which are terrains that have very controlled conditions for non-convexity. So we have like these families of terrains for which we can solve the problem exactly, but not in general. So why this is? The thing is that this problem, the shortest descending path, is related to another well-known problem, which is the weighted region problem. The way of thinking about it is you have a 2D terrain split into regions, and each region has a cost for traversing it. You can think of it like traversing sand is more difficult than traversing grass, and of course, traversing water is very difficult, and you want to go from S to T while spending the least amount of time. This is a very natural problem, very physics-based, right? It's very reminiscent to the path light follows. And it was shown in 2014 to be unsolvable due to algebraic reasons. This is similar to the shortest descending path because both the shortest descending path and the weighted region problem are sub-problems of a larger problem, a more general problem rather, that's called the shortest isotropic path, which is this problem in which you have a terrain, and in this terrain, each face has this distribution of discrete sections in which moving in a certain direction has a different cost. So, for example, the weighted region problem would be the particular case in which every region has the same cost everywhere in every direction, and the shortest descending path would be the particular case in which every region has a cost infinity to go up and cost 1 to either go flat or go up. So, this is why these 2 problems are related, but this does not mean immediately that the shortest descending path is unsolvable. But we first need to define what does it mean to be unsolvable due to algebraic reason. because a problem is only unsolvable relative to a computational model. So we need to specify this. What computational model are we talking about? Well, the model we're using is the algebraic computational model of rationals defined by Vaya in 1988, for short ACMQ, which is a computational model that allows for arbitrary precision over rational numbers, allowing for field operations and the extraction of nth roots. This might not seem natural, but it's very natural because this is a bit of mathematical folklore. The compass and straight edge model used in antiquity is precisely the model that allows to compute numbers using field operations, addition, subtraction, multiplication, division, and square roots. Because basically everything is the solution to a quadratic. Which means that this ACMQ is like a generalization of this model. It's a very natural model for computational geometry. We will show that the problem, the descending path problem, is not solvable within this model. And we do this by proving that there exist instances with only 3 triangles. We don't need very complex examples for which this problem is unsolvable within this model. We also show that for the 2 triangle case, this problem can always be solved exactly. Okay, so consider 3 triangles, and we want to find the shortest descending path from this vertex to this vertex. One quick observation is that inside of a triangle, the path is always a straight line. And if we parameterize the path with where on these edges we cross, we can define the path uniquely with just 2 points. Also, if we have multiple descending segments, one after another, this is equivalent to finding a single geodesic. And the problem of finding a geodesic was shown by Chen and San to be solvable in polynomial time. And if you have multiple segments that are parallel to the level curves at the start or at the end of the path, you can just project the point forward and then just solve the rest of the case normally. So now we can analyze for the 3 triangle case all possible combinations of descending and parallel segments and what they reduce to. So, of course, if you have that the 3 segments are parallel, that means the 2 points are the same height, so that's trivial. If you have 2 parallel segments followed by a descending segment, you can just project this point forward 2 triangles and then just connect these 2 points. If you have a descending and a parallel segment, you can project the start point over here, project the end point over here, and then just connect the 2. If you have parallel descending, you can just project the start point here and then just find the geodesic connecting these 2 points. If you have the descent parallel case, you can just project the end point here and then just connect these 2. If you have the descent parallel case, you just have to project the end point here and then just find the geodesic. And of course, if you have 3 descending edges, that's just a single geodesic. You might notice that the EGC is missing. That is because this case is irreducible. Because the parallel segment is right in the middle, it's not obvious where we could do this projection, even if we could. So, if we want to find a counterexample, we for sure have to look here. So what we did is create a particular instance for which the optimal path is of this form: descent, parallel descent. All vertices in this terrain are integer coordinates, so we're not doing any weird tricks, we're not doing any wild stuff. And because every path is described uniquely by where they cross these 2 edges, this is a two-variable optimization problem. We can just write explicitly the distance function, take the derivative, set it equal to 0, and we find that the optimal path goes through this edge over here at a fractional position equal to the smallest root of this polynomial, which is very scary. So, why is this interesting? Well, let's introduce a bit of Galois theory. Galois theory is this mathematical framework that connects file theory, which is the study of sets with addition, subtraction, multiplication, division operations. And group theory, which is the study of symmetries and composition of symmetries. And this is the Abel-Ruffini theorem that says that some polynomials of degree greater than or equal to 5 are unsolvable using field operations and inference. And when I say unsolvable, I mean that their roots just cannot be expressed. Just with these operations, you don't have enough expressive power to write the solutions to these polynomials. And Galois theory provides a framework for showing which polynomials are unsolvable. In particular, if we take the example we defined just a moment ago, using Galois theory, we can show that the permutation group of the roots of the polynomial is S8, which is as general as it can be, which basically means that our polynomial is as bad as it gets. It's unsolvable, totally unsolvable. Okay, so this is sufficient to show that the shortest descending path problem is solvable for the three triangle case. For the two triangle case, we can do the same combinatorial analysis we did before and see trivially that every case is easy to solve. So right now, what can we do? Well, we can try to work out for which classes of the range is this problem solvable exactly. And we know that general geodesics are always solvable, as was proven by Han in 1990. We also know that if a path begins and ends with segments parallel to level curves, the path is just as solvable as the path in between them. And this is something we have not seen yet, but if a path ever hits a vertex V, if a path from S to D ever hits a vertex V, it's solvable if and only if the path from S to B is solvable and the path from B to P is solvable. And here we can see an example of why this is. Basically, hitting a vertex is just a reason. So this makes it easier. So we offer a conjecture which says that all families of terrain known to be solvable have shortest descending path of this form, where the P represents 0 or more path segments parallel to the level curves. G represents a geodesic between 2 points. V represents a vertex of the terrain that just happens to be hit by the path at a particular moment. And this is a regular expression, which means that this clean star means that this block can be repeated 0 or more times. So in fact, we actually have we have the conjecture that all families of terrains known to be solvable always have shortest descending paths of this form. And we have a theorem that says that if your terrain always has a shortest descending path of this form, then the shortest descending path problem is solvable in polynomial time. So to conclude, even for the three-triangle case, the shortest descending path problem is untractable. This is not really a computational challenge, this is an algebraic one. We can show that for the three-triangle case, there is only one particular type of path that is impossible to solve. And for the two-triangle case, all paths are possible, all cases are possible, solvable, sorry. And be careful when trying.
Thank you, Victor. Any question?
If you go back to the slide before, your algorithm has PGPV. Does that mean that in the picture you show, you go from parallel to geodesic to vertex immediately? Does that mean that the parallel is
here represent 0 or more path segments parallel. So 0 path segments is valid. Yeah, I was expecting that question. Maybe not the clearest picture, but yeah. Any more questions?
Any more questions?
So in the last slide you mentioned untractability, before you mentioned unsolvability. Is this now meant in the same way, or?
In this context, I'm using them as signage, yeah.
But see, for me, the question, okay, the tangents were disturbed, like taking inputs is not enough. There are enough packages now to deal with algebraic numbers. Can get roots or roots or whatever roots of polynomials. And then the real question becomes, if you want to compute those those paths, what is the algebraic complexity of those numbers? So what degree polynomials do you get? How do the coefficients grow? You don't seem to.
I'm not sure, but I think the degree of the polynomial can grow arbitrarily large.
Well, arbitrary long paths, I'm sure. But
Yeah.
then depending on, I'm sure some bounds would be possible. It's like in various parameters. In particular, we have the 3-ish example where I don't think the degree will be arbitrarily large. So
Yeah, for the 3-triangle case, you can actually show that this variable case, the 8-degree case, sorry, is as bad as it gets.
Okay.
This is, for the 3-triangle case, this is the worst you can get.
Does it help if your points are like uniformly distributed, for example, in fields? Is it then?
What do you mean? So,
Like if you, for example, if you do from the top, then all your points are on the gate.
sorry, I can't hear you.
So if you, all your x and y coordinates are, for example, integers. And you just have a grid on the x, y, so you only have a height difference.
Sorry, if all your coordinates are integers, all of these coordinates are integers.
Yeah, that's what I mean. That like the projection, right? You get a grid.
So if the projected length is all integers, what do you mean? Or?
Sorry.
I'm not getting you. Sorry.
You have a triangulation of a grid.
Yeah.
You take a grid and then you lift it. So in this case, half.
So you lift it. So you flatten it. You mean or what?
No, so you have a grid,
Yeah.
and then for every point of the grid you have a height, this, and then you triangulate, then you get a terrain. So for this type of terrains.
I think it's also difficult. I'm not sure, but I think it's probably also difficult. Like, I'm not totally sure, but yeah. Like, I can assume this can be approximated quite well with a grid-like projection. Yeah, I think so. I think it's also difficult.
Oh, okay, I have one question. How did you manage to get the actual integers to the counterexample for the construction? Computer search, I would presume.
If I told you that this was my first try, like I actually had an idea of how this had to look, right?
Okay.
I had to have something that was descending, then something that this vertex had to be a little bit up, so you wanted to go parallel, and then you want to descend. Just knowing this, the first example I tried, which was this, worked.
And then you hard-coded the coordinates in order to get the picture you wanted to get, right?
Yeah.
So this might also suggest that with high probability,
Yeah. In fact,
any of them would be
this was
solvable, right?
also a conjecture we had. Right?
Yeah, okay,
This is,
nice.
Yeah, this is with high probability impossible as well.
Yeah, well, if no more questions, then thank you very much, Victor.